Hi everyone, hope that you're all doing well. In this video, I'm going to show you how to conduct a data analysis project in the case where you've got both a qualitative predictor and a qualitative outcome using Stata. I'm going to start by running our standard header here. I explained what all of this means in a previous video in this series. Please go see that if you are curious about why we conduct any of these operations here. I do want to highlight one point here, though, which is that you should make sure that you are in a folder that you consider your working directory for whatever project you're working on. That's what this command means here, this cd. So you should make sure that you have changed your working directory. That's what this command means, to a place where you want to pull data from. So you should make sure that this folder contains the data set that you're using. I'll be using the GSS 2018 wave, but you could use any set of data that you like. Unless you're using data that ship with Stata, such as the auto data set, you'll need to either click on that data set when you get it, which is fine, but a kind of haphazard way of going about things, or you'll need to make sure that the data are placed into your working directory, which is this folder here. This is just a folder on my desktop that I've made. I won't go too deep into the details here. Again, see that other video, but I just wanted to call attention to that fact because it's the most important part of all of this stuff here. So let's pull in the data, and then we'll get started. So you can see that we've loaded successfully the 2018 GSS. So we'll begin our analysis here with a really simple case where we've just got two qualitative variables that we're not going to modify very much. We've got one variable that is a classic nominal variable, in this case religion. And we've got a variable that's a little bit simpler and is pretty close to being a dummy variable. We'll come back to the dummy variables in a little bit. So it's significantly more concise or compact variable, which is one's opinion of capital punishment in the case where the defendant has been convicted of murder. So we're going to go ahead and inspect the variables individually. So we'll conduct the univariate analysis, and then we will go ahead and put them into relationship with one another, or rather seek to uncover the relationship that exists. So we'll go ahead and run this comment here. Again, for material on things such as comments, please see a previous video in the series. So we'll find it fairly easy to conduct univariate analysis for qualitative variables. So in this case, let's begin by just pulling up some very basic information about religion. So we'll write codebook relig, and we'll pull it up in the GSS here. And we'll see that it's a variable that is technically speaking numeric, although all that means is that there are just numbers assigned to these qualitative outcomes. That doesn't mean that this is a truly quantitative variable. Stata can't tell you that. That's a decision you have to make as a researcher, someone who's got some kind of expertise or substantive knowledge of the situation. All that means that for us, basically, all this numeric means is that there are these numbers assigned to the possible values. And by the way, it is conventional to call Protestant or Catholic values, even though they're more like statuses, for instance. They're not really values in the numeric sense. We could have a variable that's what's called a string variable, and that's really actually a distinction in computer science rather than in social science. Pardon me. And a string variable is one where there just aren't numbers assigned at all. So you might just have words, basically. That might seem like a more natural way to deal with qualitative variables at first, but there's a lot of routines in Stata, but also in programs such as Python, where it's actually inconvenient to have no numbers assigned to the variable, even if it is qualitative. So we won't actually encounter a lot of string variables in the GSS, but that is something that happens in real life. Usually people find it a bit more of a drag than not. There are some rare cases that have come up in my experience where it's actually convenient to convert or to keep a variable as a string, but those are infrequent. Anyways, the takeaway for this presentation is that you shouldn't be misled by this. This is just basically a distinction in computer science rather than social science. We can also see the value label here. We'll come back and look at that later. We can see that this has got a lot of possible values. So what that means is that we may want to consider later on somehow compressing the information enclosed in this variable into a smaller number of possible values. And we can see that we don't have very many missing values here, and that's a good thing. A lot of times people don't pay close enough attention to missing values when they are looking at data analysis or conducting a data analysis, and that's generally speaking an underemphasized topic in the field. But that said, it's also kind of a higher level thing, and so we won't be able to tackle that today. If there's missing values, I'll just say this briefly, if there are missing values that are truly missing more or less at random, some people just arbitrarily decided not to respond, it's not such a big deal. Your sample size is just smaller. But as you probably can guess, there are, generally speaking, reasons for not answering questions that have quite a bit to do with other kinds of information about a person, and that means that we have a bit of a biased sample. We no longer have a simple random sample, pardon me, or even a stratified random sample. Basically, the random element has been in some ways compromised. So we'll come back to that in maybe a future class, but not in this class, unfortunately, although I'll discuss it at certain points. But for now, basically just know that you should be a little bit cautious about making really strong claims. So let's go ahead and tabulate religion. And this is going to produce three things here. So it's going to produce the raw frequencies, as you can see up here. And we can see we've got, majority of the sample. If we compare this to this, Protestant, Catholic are next up, then none are next up after that. But Stata also just goes ahead and prints what is effectively a kind of estimate of the population probability mass function. In other words, a function whose value for a given value of x just tells you the probability of that value occurring. That's what's printed here, basically. So we can see that if this is a good guide to the population, there's about a 49% chance that someone is a Protestant. We can also see the cumulative distribution function here, although as I note in the commentary in the do file, this is not a very meaningful, it's hard to even really call it a true cumulative distribution function because the function itself will change if we reorder the variable and there's no necessary order to these variables, these values, pardon me, this is a true nominal variable. Okay, so that's basically all we need to print for the numeric side of the qualitative analysis. We're just interested in getting a picture here. I would say this column and this column are the most important ones. This isn't really meaningful on its own, but someone might be curious to know if you say make strong claims about what people who adhere to Buddhism think in your sample. The reader might be curious to know, well, exactly how many Buddhists did you actually encounter? And you would be remiss not to tell them that it was fewer than 20. So that is sometimes worth pointing out. But if you have a really, really large sample and you report the overall N, sometimes you can leave this information out. But these two things are generally speaking good to produce. Okay, so let's look at a basic bar graph here. And I'm actually just remembering that I forgot to change my scheme back to the default. So let me go ahead and do that now. I'll explain schemes later on. So we'll pull up a bar graph here. Note that the syntax is kind of unique. So we'll write graph bar comma over relig. And that's because the bar graph command actually generally expects a quantitative variable as the main argument to the function. If we put relig here, which I'll show in a moment just because it's a common bug, we're going to get basically the mean of religion, which is very uninformative. So here's the correct syntax. I'll show in a moment what happens when we don't do that. And if we do this here, we see that this is actually not looking so good. There's quite a bit of messiness on what is effectively the x-axis, although it's not really an x-axis. But Stata isn't going to fix this for us. So we need to somehow figure out a way to improve upon this. And there's a couple of things we might want to try. One is that we might want to make the bar graph horizontal, which is completely allowed. And the second is that we may want to go ahead and think about sorting the values of the variable by their height, basically. So which are the most probable, and that'll make the graph a little bit easier to look at. So let's go ahead and do that now. And you can see here that Protestants are the most kind of prominent or the most probable outcome, followed by none, then Catholic, then Jewish, then other, and so on. I won't bore you by enumerating all of those here. But this makes the graph, I think, significantly easier to interpret. Now, we should still put in things here, such as the title, the source, the sample size, but I'll come back to that later on at the end of the video. You should do that for every graph that you produce, but I don't want to spend all the time explaining all the code for that for every graph, and right now we're focused more on the numeric analysis. So that's that. I did promise that I would show what would happen if we mistakenly wrote relig right as the main argument to graph bar. So let's do that now. And as I mentioned, this is just going to produce a mean. Now, of course, the mean is utterly meaningless in this situation. It would change wildly if we, for instance, reverse the order of the values of relig. And so this is just a mistake. So make sure to avoid this. And this happens every year. Some people get a little bit mixed up about this, and it is very confusing, admittedly. So the graph bar syntax here is just a little bit different than some other commands in Stata, but you want to make sure that you write comma over relig to get a most basic version. For some variables, we'll see one in a moment, you don't even need to do this h bar business because the main bar graph default will look fine. And you don't need to enter anything after graph bar or graph h bar. Okay, so that's that more or less. Now let's do the same thing for capital punishment. So we'll look at the code book, and we see here that, again, it's got this somewhat confusing initially numeric thing, but we've already explained that. Notice that this is on the way to being a dummy variable, aka indicator, binary, Boolean, Bernoulli variable. So many other names are possible as well. But basically what that means is that it's only got two possible outcomes. Now, these aren't coded in the traditional way. So these are coded 1 and 2, not 0 and 1. And for some applications, that does have some meaning, but we'll come back to that later on. There's relatively more missing values here, but still not too many. If you do see quite a few missing values, you may want to inquire into the source of that missingness, but this isn't terrible. And that's more or less all we can glean from this. So let's go ahead and look at the frequency table. So again, the percent column is going to be, broadly speaking, the most useful. And that gives us, again, something that's like an estimate of the probability mass function for the population. And we can see that, generally speaking, people were more favorable towards the death penalty in the case of people who were convicted of murder and they were opposed to it. The cumulative frequency column here is a little bit more meaningful because there's only two possible outcomes, and these are ordinal in a sense, so it's not quite as meaningless, but we should still be careful reporting it. Generally speaking, this is more informative. The frequencies, again, are worth reporting, but if they're not tiny in either direction, as long as you report the overall sample size, people may not necessarily care that much about the frequency. Finally, we can produce a bar graph as well, and as I mentioned before, this is a case where you actually don't really need to toggle it too much because it looks more or less fine on its own. Now, let's go ahead and proceed to the bivariate analysis, because the univariate analysis for qualitative variables is, generally speaking, a little bit simpler. So the most obvious choice for doing a bivariate numeric analysis would be to conduct a two-way table, sometimes called a cross-tab as well. And so we're going to pull up the table first with the raw frequencies only, and we see that this is the output that we get. We could go ahead and calculate percentages by hand. So for instance, we could calculate row percentages, aka conditional probabilities, by looking at Protestant, for instance, and then calculating the probability that someone in the sample favored versus opposed the death penalty. And of course, that would just mean dividing this by the total and then this by the total. We could also go down the columns. I'll talk more about that choice in just a moment. But we might as well have Stata do it for us. Now, I wanted to note one thing before going further, which is that until we do calculate those percentages, the choice of which variable to assign to the rows versus the columns is aesthetic. So we could assign it in the inverse way. Now, what I mean by aesthetic is that in some cases it won't look very good at all. And that's exactly what's happened here. So we can see that this output spills out over many lines in Stata. And so that provides us a reason to prefer the prior way of doing it here. So this is how we should, in this particular case, think about presenting the analysis. But in other cases, it'll be really dealer's choice. So that's that on basically choosing rows versus columns. Now, again, once you do select one method, then you're a little more constrained. So what we should do now is calculate those percentages. And formally speaking, those are known as conditional probabilities. In other words, this is how you read this notation. We want to calculate the probability of observing some particular outcome of y. So observing that big Y, the variable, equals little y, some possible value. given that x, big X, the variable itself, is equal to some particular x, little x. So we can do that by just adding percentages. Sometimes people call that percentage in the table. By adding the options row or column, or even potentially both, to the basic command for a two-way table. But generally speaking, we should focus more on the variable that's causal. And in this particular case, I think it's a pretty straightforward story. So religion more likely causes your opinion on capital punishment than the reverse. Now, anecdotally, even in my own kind of broad social circle, I can think of cases where people did change the specific variant of religion that they adhered to because of disagreements on social policy. But we might think that the more general story is that religion tends to exercise a greater influence on your opinion of specific social policies than the inverse. So let's calculate row conditional probabilities with religion on the rows. And the general syntax for tab here is tab row var call var. So here religion is on the rows again. And if we do that, this is maybe a little bit challenging to look at, and we'll come back to that later on because there are so many values of religion. But we can see that this gives us something like a fairly coherent story about how different religions praise the death penalty. So Protestants, generally speaking, favor it. Catholics, a little bit less favorable. Those who are Jewish is sort of in between the two. Those who select none, maybe kind of predictably, or those who selected other. So religions that might be somewhat outside of kind of the mainstream opinion in the United States, possibly a little bit more heterodox in different respects, are a little bit less inclined to believe in the death penalty in this case, although it's a fairly modest difference, and we should pay attention to the sample size. We actually aren't yet going to talk about inference. That'll come up very soon. We should know that these subsample sizes are relatively small, though. And we can see that there's a pretty pronounced variation here. So for instance, although this is a very, very small subsample, those who mark down that they are adherents of Hinduism, people were generally speaking quite opposed. And then for people who answered Native American, of course, this is a tiny sample, so we can't, put too much onto it. But technically speaking, the conditional probability conditional on you answering that your religion was a variant of Native American religion, your conditional probability of opposing the death penalty was in fact 100%. So that's the basic analysis here. Now you can see already that we may want to somehow condense some of this information here because we saw that we were going through the laborious process of looking at all of these religions, but in principle, this is the right approach. I did want to make one point in passing here. So you could calculate conditional probabilities going the opposite way. What that means is that you could calculate conditional probabilities on the death penalty and then select religion as the outcome. So here's how we would do that. We'll keep the same orientation of the table because we saw before that that was aesthetically more appealing. So we'll say tab, relig, cat pun, but we'll write column instead. And notice that this now calculates column conditional probabilities. In other words, it calculates the conditional probability of you adhering to a particular religion conditional on your opinion about the death penalty. Now, this, generally speaking, is less informative for two reasons. The first reason is that this is not as intuitive unless we know the marginal distributions of religions. For instance, if I say that Protestants are 51% of those who favor the death penalty, but 45% of those who oppose it, we don't necessarily know if that is disproportionately in favor or opposed until we compare it with the marginal distribution here. So Protestants are 49% of the sample, so at 51%-ish of the favor, they're overrepresented. But to a lay reader, this type of comparison may not make that much sense, or it may not be as intuitive. Why was this one more intuitive up here? Well, it's because we kind of have a natural baseline in thinking about social policy that 50% of a group approving or disapproving of a thing generally is like a reasonable kind of bit of, maybe you could say a prior, which is a technical term sometimes in statistics, but here will just mean that it's maybe something that you might come into the picture thinking. But in this case, it's a little bit less intuitive unless you have a really keen sense right away of what the overall or again, to use the technical terminology, the marginal distribution of Protestantism is. And by the way, marginal distribution literally just stems from the fact that it's in the margin of the table here, or we've got the marginal distribution here. Now, these percentages aren't informative because we've calculated column conditional probabilities, but we could look at these raw frequencies, and this gives the marginal distribution of favorability and opposition to the death penalty. So we could calculate these conditional probabilities here down the columns, but it's not quite as informative. Again, it doesn't do anything that's incorrect, and I actually have a fairly rigorous technical proof of this fact using Bayes' theorem in my lectures that are linked in the notes to this presentation. So it can't be the case if Protestants, generally speaking, up here are more favorable to death penalty in the case of murder than is the overall population. So 63% of the population favors it, 66% of Protestants favor it. That must be, generally speaking, consistent with the fact that Protestants are overrepresented among people who favor the death penalty. But, and I'll spare you the kind of technical details, you might be interested to know this. Generally speaking, that's still consistent with some results that might be kind of counterintuitive if you're thinking about calculating column conditional probabilities. So Protestants are almost a majority of people who oppose the death penalty in the case of murder, which would, when you put it that way, kind of give the wrong impression, unless you're making sure to compare that to the total probability here. So, or in other words, marginal probability. So Protestants in that respect are actually underrepresented. 45 is smaller than 48. They're overrepresented among those who favor it. But again, to the lay reader, that may not be the most obvious comparison to make. So that's just a note on inverse conditional probabilities. So let's come back and mention another complication. We already saw before that that two-way table was a little bit messy. And it was a little bit messy because there were quite a few possible values. And there's also some considerations about surveys there. So many values of the variable are problematic in a certain sense because the GSS and many other surveys stick with the same division of variables that they've always used. So sometimes you see things such as, for instance, an outdated spelling of Muslim. So if we tab religion here, you can see that they've spelled it in this way. So there's a whole variety of reasons that we may want to try to somehow condense that religion variable. And I'm not saying that you should do this just for the sake of making your project easier, but one thing that's often true is that people start data analysis projects without really understanding what it is that they're really interested in, and that tends to develop over time. It's a bit of an emergent process. So you might, as you go about your project, realize, well, I'm really interested in this specific pairwise comparison. And I'm going to kind of assume that that's true in this particular case, just to make the point and to show you some techniques that are useful. So what if, in this case, we're just interested in the distinction between Protestants and all of the religions? That's not as arbitrary as it might seem. For instance, the noted sociologist Max Weber, not someone that I'm personally a giant fan of, but nevertheless someone who's very prominent, or was, I guess, had a very strong kind of thesis about the unique role that Protestantism played in its interaction with the development of capitalism, particularly in the US. So we might be interested in a project that distinguishes between Protestants and all the groups. And Protestants, as I mentioned here, is still kind of a problematic category. But if you really do want to test the hypothesis that Protestants differ systematically from other groups, this would be the way to do it. So you can probably see where I'm building here if you've heard of these terms before. We'll need to make a dummy variable. And so we're going to use, in this case, a fast way to construct a dummy variable, although in the linked lecture slides, I link to a reading from Rachel Gordon, whose book Regression Analysis for the Social Sciences is a nice intermediate text. And she shows a much more painstaking way that also, however, might be more kind of familiar feeling for people who are new to this stuff, but it is also very, very slow. So there's benefits and drawbacks. In the past, when I've taught this material, I've taught the slow way, but I wanted to show you this time a faster way. And so to make a Boolean variable, we might as well go ahead and use Boolean expressions. And by the way, bool George Boole was a logician, kind of proto-computer scientist, someone who really pioneered the algebra, basically, of binary variables, which is why we call those variables after him. And in general, made quite a few contributions to logic, and had some interesting relatives as well. His daughter, Alicia Boole Stott, was kind of noted what people will call an amateur mathematician in her own right. So she wasn't a professional mathematician, but actually made some fairly important contributions to mathematical theory. So I just kind of mentioned that in my general interest in mentioning the contributions of marginalized groups to mathematics. So her work is super interesting. Allegedly, she could visualize 4 dimensions effortlessly, which is something that if you've ever tried to do that yourself, you may have found kind of problematic. I have a couple of tricks for doing it myself, but they took quite a while to learn. So I'm jealous of people who can do it effortlessly. Anyways, that's a bit of an aside on Boole and the Boole family. So here's how we go ahead and make those variables. First, what we're going to do is tell Stata to make a variable that records the responses to the logical statement, religion is equal to 1. And notice that this double equals here is really important. So in computer science, not always, but this is a very common convention, a single equal sign, like this one down here, means assignment. In other words, when we say gen Protestant equals relig, we're telling Stata to generate a variable called Protestant that is equal to relig and then some other stuff. What's the other stuff? Well, the other stuff is if this condition is true. And so the double equal sign is evaluative. In other words, it means Stata should go ahead and see whether this condition, pardon me, is true. I wanted to go back. I'll say a little bit more about that in a moment. I wanted to explain this bit here really quickly. So why am I writing this particular condition? Well, it's because what I did before I made the video many years ago was go ahead and describe this variable and obtain the value label here. So it's just relig. In GSS, it's oftentimes just the variable, but in all caps. And a value label is a place, we'll see one in a moment, where Stata actually goes ahead and records a mapping between numeric values and string values. In other programming languages, this is called dictionary or a dict. So we're going to go ahead, pardon me, and list out this value label. So we'll do that now. And we can see the value label here for relig. And so this is what we were missing before that I kind of alluded to a while ago, where we want to get a comprehensive listing of all the numeric outcomes and the value labels, or in other words, the strings that print or many commands that they're associated with. I'm actually not aware of a better way to do this in Stata. You can sometimes kind of do a little bit of a workaround where you can, for instance, tabulate the variable. And then what you can do right after that is note these frequencies and then tabulate the variable, but with the option no lab for no label. We can just write no label added. And then we can just sort of compare. So we can see, okay, there was only one possible value that had a frequency of 32 and other had a frequency of 32. So other must be 5, but that's fairly inefficient. So we generally speaking want to use the label list command. So coming back to the main theme here, if I wanted to make a variable that has as ones only those who are Protestant, I need to go back and look at the value label and see, okay, who was considered a Protestant. And strictly speaking, if I want to avoid people who, for instance, said that they were just generally Christian, and of course, avoid other Christian denominations, so Orthodox Christian, non-denominational, pardon me, could be considered Christian, possibly, depending on who they are. Other Eastern could be Christian, etc. Catholic as well, of course. We want to also make sure that those people are not considered Protestant. So in this case, we're going to say, okay, well, there was only one possible value of relig that meant that people were Protestant, and that was when they were equal to the value of 1. So we'll notice that the numeric value of Protestant is equal to 1, and we'll write this expression here that says generate this new variable called Protestant that equals relig equal to, doubled equal to 1. And that's a Boolean expression here. And so what that's going to do is tell Stata if this condition is true, give people a 1 on Protestant. If it's false, then give people a 0 on Protestant. So let's do that now. And we'll check our work in a moment here. First, one thing we need to do is remember this important gotcha in Stata, which is that missing values are considered internally by Stata to be arbitrarily large constants. That's a unique convention. You could quibble with it and think maybe that it's a little bit silly, but that is the way that it works. So one way for this statement to be false, of course, would be if people are missing a value on relig. So what we need to do, the slightest modification here, is we need to go back and assign people who were missing on religion to a missing value here. And the reason that we're going to do that is because if we don't do that, people who are missing on religion will be assigned to 0s on Protestant. But definitely being non-Protestant is not the same thing as you having a missing value. So we should make sure that you remain missing if you were initially missing, because again, if you didn't record your religion on the GSS, you didn't tell the surveyor what your religion is, that is not the same thing as you saying, I'm definitely not Protestant. So we should be really careful about missing values when we can be, even though we won't deal with them systematically in this course. So that's what we'll do now. And then finally, to kind of prettify things here, we're going to make a value label. So just like we found the value label before for relig, we're going to do that ourselves. If we just tabulate Protestant now, we'll see that it just looks like a very simple dummy variable. And it can be a little hard to keep track of this without a value label. So we just see 0s and 1s. So let's make that value label now. Here's the general syntax. We say label, define, value I, and then label I. In other words, we'll basically write down here, like 0, for instance, then give Stata the name to print for people who are 0. We'll just say non-Protestant, and we enclose that in quotation marks. And then we do the same thing for 1. So 1s were Protestants, so we enclose that term in quotation marks. And then when we're done, we will go ahead, we'll just run this command, and then we will assign the values like so. So we'll say label values. The variable list here, we're just going to assign this to 1 variable. Sometimes it's useful to do more, probably not at this level. And then we'll go ahead and print the value label right after that. So let's do that now. And let's go ahead and check our work. And when we do that, we'll see that the values of Protestant have been converted to these strings here, at least in certain commands. They haven't actually been replaced, but for certain commands, Stata will print non-Protestant and Protestant rather than 0 and 1. So let's do that now. We're going to make a two-way table here, actually, and we're going to add the option miss. And the reason we're going to do that is that this two-way table is not actually analytical. It's a two-way table that is checking our work. And so if we come up here, here's how to read this table. We want to make sure that people who were not Protestant are every person on the original religious variable who was in some way not Protestant. And I'll give you a second here to verify that looks to be done correctly. So no one who is a non-Protestant on the new variable was a Protestant on the old, but there were a bunch of people who were not Protestants, just using substantial knowledge here, on the old variable who became non-Protestant on the new. That's good. The only other people who were not Protestant were those who are missing, and remember that we wanted it that way. Then we can also check the Protestants. So we can see, okay, Protestants seem to have come only from people who were Protestants. In other words, you were a Protestant on the new variable only if you were not one, or sorry, you were one on the old, and there's no other sources, which is good. Finally, the only people who are missing, a dot, by the way, is the simplest representation of the missing value at Stata. The only people who are missing here were people who are missing on the old. DK and NA are just value labels for different kinds of missing values in Stata. I'm not going to go into the details of the different kinds of missing values. Suffice it to say that the difference is not very important for us at this level. So that is a very good sign, and that's how we should generally check our work. By the way, I wanted to mention one thing here, which is that it can be the case that you have a variable where it's not as simple, so you can't necessarily write this Boolean expression up here like this, because maybe you have multiple conditions here. So if that is the case, you can do a couple of things. Let me show you a couple of examples here really quickly. So one would be Let's say we want to use an example I've used in class before. Let's say we want to make a variable indicating whether someone, well, let's find an example that would be meaningful. So let's just play around with, let's say, the marital variable. So we can see married, widowed, divorced, separated, never married. So let's say we want to make a variable. This is a pretty common thing in demography, indicating whether someone has ever been married. And so that's actually not just the married, that's also the widowed, divorced, and separated. Now, this actually is going to turn out to be expressible with the Boolean expression, but let's pretend that it's not. So how do we make a variable indicating whether someone's ever been married? Well, we could do it like this. So first, let's describe marital. We can abbreviate that with D. And the value label is marital, so we'll list that out. And we get the value label here. And here's one thing we can do to make that variable. So if we have multiple conditions that we want to assign to one, we can say Jen married, or ever married, would be better. And we'll actually just make this missing at first. So again, this is kind of taking this slower out, but this is the most kind of careful way to do it. So we see this creates a missing value for everyone. And then what we're going to do is say, I want to replace the value of married, and I want to assign it to a 1 if marital was equal to 1. Oh, sorry, that was ever married. And then I can just iterate that process. So I can say 2s, I want to also be registered as 1s on ever married. So we'll say replace ever married equals 1 if marital equals 2. And then we can keep going on. And then when we get to a value where we don't want that to be true, we'll say replace ever married equals 0 if marital equals 5. And because we started by making this variable missing, we don't need to do anything about the missing values. We would then want to go in and put down that 3 and 4 should also be considered 1s on ever married. But that's a way to do this if you do have multiple conditions that you want to assign in different ways. There's a way to do that also with the recode command in Stata, but this is a pretty foolproof way that forces you to think pretty rigorously about what you're doing at each point. So I think it's not a bad idea to consider just doing it in this simple way. Okay, so coming back to the main point, let's go ahead and think about what we would make of the summary statistics for our new dummy variable. So these are actually fairly easy to interpret. You might recall that the sample mean is the proportion of people in the sample whose outcome on the variable is 1. And the variance is very nearly p, which is the probability or the mean, times 1 minus p. There's a small bias term, n over n minus 1. It asymptotically approaches 0 as n increases. You can see my lectures if you really want to know more, but that's just meant for a little bit of intuition and then a proof that's kind of important, but not relevant to us right now. So let's go ahead and look at that variable. And we should see that the mean of Protestant is also the same thing as the proportion of people who were Protestant. So here we see 48.9. If we tab our original village variable, we can see this is 48.95. And up here we see 48.9. We shift over the decimal, and this would round to 5. So we're in good stead there. We can't actually see the variance directly from a simple set of summary statistics, but we could obtain that this way. So we could say sum Protestant D, and the variance is printed here. And if we really wanted to, we could go ahead and prove using return values that this is in fact p times 1 minus b times that bias term. So we could say display, we'll write all this out even though you could abbreviate it. And then we'll say return the mean. And by the way, this only works if you have just run the command to which these return values apply. This is kind of like using the answer key on your high school calculator. So we'll say display r mean times 1 minus r mean here. And then we'll say times r n divided by here r n minus 1. We'll double check that we've got all the parentheses right. And you can see that we actually get more or less the same exact thing from the variance here. So if you want to see what kinds of values are possible, what kinds of return values are possible, you can always write help. And in this case, we'll write sum and scroll down to the bottom. And when we select the detail option, see detail only, here we have all of these things here. So that's kind of nice. I discussed return values a little bit in more detail in the variable and quantitative variables. It's not as important for qualitative variables, but it's kind of worth noting as a Stata feature. Delete this here. Okay, so that all checks out. Now let's go ahead and just turn and look at the simplified output here. So let's go ahead and create a two-way table with conditional probabilities on the rows. And we'll come out and look at the output. And you can see that this tells a little bit easier story to digest. So we see that Protestants, generally speaking, favored the death penalty in the case of murder at a rate of 66% to about 34%, while non-Protestants as a whole were about 60 to 40. So there's a significant enough difference here. We'll learn later on in a different lecture in this series basically how to test this. We would use there's kind of a couple of options. We could use a two-group test of the difference in proportions. We could also use the general chi-square test, but we'll come back to those later on. There's quite a few other tests that would be appropriate in this case. But for now, we can just use our intuition that this is a reasonably large difference, not giant, of course, but we might infer that it's unlikely to be purely due to chance. We'll, again, think about that later on. We could actually just very quickly add the chi-square option, and we'll just get a brief sense. I will just interpret this output for us and see. I've never actually thought to check this because I use a different example when we come to inference. So this ends up being, we have a small p-value here. So conditional on a whole bunch of other assumptions, this is unlikely to be due to chance if the variables have no relation, in fact, that is. So that's our basic conclusion. Let's wrap up by looking at a graphical analysis here. And what we're going to do is use a spine plot, aka a mosaic plot, which is a highly informative graph, but it is an instance of a graph that is not actually part of Stata's default routines. And the kind of infamous Nick Cox, who's a very prolific Stata programmer, someone who maybe has a reputation as being sometimes a bit prickly, but is also truly a genius of this software, wrote a routine that works really nicely to produce what is sometimes called a mosaic plot, also sometimes called a spine plot. In Stata, it is called a spine plot. So we're going to learn an important technique here, which is installing a command, which is something that in many languages, R and Python included, you don't necessarily install commands, but you very often have to attach libraries. So if you talk to people who use other statistical software, they'll probably think nothing of this. In Stata, it might seem a little bit scarier because we don't always do this, or we don't do it very often, but there's plenty of times where we do. So let's install the spine plot command here. And we write SSC, and that actually doesn't refer to the SSCC if you're watching this from the UW-Madison, just a linguistic coincidence, although they both involve social science, I think. Actually, no, this is for statistical software, so that's just a purely linguistic coincidence now that I think about it. Anyways, this basically tells Stata to connect to a remote server and install this command that's stored on that server. If you've already installed it, this won't create any problems for the most part. On very rare occasions, this will, but don't worry about it for the most part. So we see that all files already exist and are up to date. So no updates to this command since I last ran this code, and we can just go ahead and start using it. So let's take a look at it now. And we can see that this is a really nice graph to look at. So what this does is, unlike many bar graphs, this gives us some information about the marginal distribution of the predictor here. So it's kind of hard to see because Protestant and non-Protestant had almost the same probability of proportion, but technically that's what this is showing here. Let me show a more extreme example. Try spine plot, and let's just sub in race. So we'll say cat pun race. And ignoring the GSS's annoying default categories, so they are really lumping way too much here, but you can see that in this particular case, the spine plot does actually give significantly more information. This is the marginal distribution of race here. But coming back to the example that we actually wanted to use, we can see that it gives this marginal distribution, and then it also gives the conditional distribution of belief in the death penalty for murder. And this visually confirms that Protestants, generally speaking, were more favorable to it. It doesn't actually give the marginal distribution of this here, which might be kind of nice to have, but we can infer that it's got to be between these two values here, which we can confirm using some Very simple algebra, although I won't walk through it. So that's more or less what we like to see. Now, I did want to make another pitch for dummy variables here. So if we did go ahead and try to use our original variable, again, don't do this, but this is going to produce some really difficult to interpret output. You can kind of get the basic story, but even as soon as we get past Protestant, Catholic and Jewish are overlapping here. So what I would recommend is do not do this. If you get output like this, consider making a variable that at a minimum condenses the information about these two variables. And you probably want to go ahead and just consider making a dummy variable, unless you're really sure that you want to make several pairwise comparisons. Okay, so that's that. Now, notice that spineplot went ahead and nicely interpreted the values of catpun, but not all commands are going to do that. And so catpun is not actually here a true dummy variable. We saw before that it was actually a 1 and 2 variable. So I wanted to introduce you to this other syntax, and this is yet another way of making a dummy variable. Here, we're not going to do too much because this is already very close, but one thing we're going to do is use the recode command, and we're going to basically follow this syntax. So we'll say recode old variable, numeric rule number 1. So assign old value equal new value and then give it this label. And then we can add on additional rules. And then we'll have a comma. And then we can say replace or gen new var. And generally speaking, you should generate the new variable. So let's put that into practice. That was awfully abstract. We're going to write recode in this case, catpun. We'll say keep 1 equal to 1. We like that part. And we'll say let that be called favor. But we want to make those two 0 in order to make this a true dummy variable. And we'll make those people oppose. Then we'll generate a new variable called death penalty. And we can again check our work in the same manner as above. And you can see here that people who, in this case, oh, sorry, this is a bit of a problem here. This should actually be catpun, pardon me. So in this case, this looks a lot better. You can see that people who, this is slightly annoying, this variable has been labeled in this long way, but you can see we've got people who are on the death pen variable. They opposed only if they opposed, they favored only if they favored, and they were missing only if they were one of these values that are missing. So that is good news. So now we can go ahead and interpret our variables, meaning the same way as above, but we couldn't necessarily do that with catpun because it wasn't a true dummy. That's not always a big deal, but in many cases, you should try to use true Boolean variables, especially if you have ones that are already close to Boolean variables. So let's go ahead and wrap up by toggling our key graph a little bit. I explained the fundamentals of this in the publication quality graphics video, but there's a couple of things here that are a little bit specific, and I do want to review these techniques in a different setting. So the first thing we're going to want to do is actually fix that value label. So we saw that the death pen value label is this thing, and that's a little long. We don't necessarily need to tell the reader that it's a recode of an old variable. So let's label the variable this way. We're going to say label variable death pen, and we'll just give it this more intuitive label. And that won't produce any immediate output. But one thing we could do is just describe death pen, and you can see that it prints this more informative label. Now let's talk about schemes a little bit. So I went over this in the publication quality graphics video, but schemes can be really fun to play around with, and they give you a little bit more control over how your graph looks. And to be honest, the Stata default is not that great looking. Stata is a really cool program overall, and I would say I only developed that opinion after many years of using it and getting more used to, for instance, other types of software that are out there. But once you see some of those others, you might think, we should maybe try to do a little bit better with Stata. So R, which is a competing software to Stata, I think generally speaking, has better aesthetic properties. So one thing we can do here that's a generally useful thing is learn another way to install new commands, or in this case, new schemes. So I located a scheme for Stata from this fellow here. It's on his GitHub that imitates those of R. So let's install his scheme pack here, actually. And then we're going to set the scheme to gg_q. ggplot is the plotting routine in R, just in case you're curious. And then we'll set the scheme here. And now let's produce the graph. So I want to show you the graph first. I'm going to let this finish here and fix a typo. I'm going to show you the graph first and then explain what all of this does. So this is relatively nicer than Stata's original setup here. So we can see that this gives us the relationship between religion and opinion of death penalty. You see whether someone is non-Protestant or Protestant has some effect on their approval of the death penalty in the case of murder. And we can also see that Protestants, generally speaking, were just about half of the population. We get the source, we get the N, and we get a little bit of a note here about what this actually means, opinion of the death penalty, because this is not in general, it's for cases of murder. So let's show how I produce that. So I'll come back to this bit here, actually. Let's put a space there just to emphasize that these are not actually directly related. So what did I do? First, I wrote spineplot, the basic command, and then the variables, just as we did above. Then I add a comma, and I start agglomerating some options. So I write title first, so I write this title here. And notice that the title goes in quotation marks, as you might predict. And then within the title option, I add a sub option, which is that I want to make the size a little bit smaller because a lot of times, for whatever reason, Stata just tends to print titles too large, in my opinion. And kind of objectively, because once you start combining graphs, which is a pretty common task, the titles are just clearly too big. They spill off the page. So for whatever reason, that's Stata's default, at least on my machine in my version. So we can specify that the size should be medium. And remember here that these line extenders are important. Stata, among other pieces of software, such as Python, will generally speaking regard the end of a line as the end of a command or end of a set, basically the end of like a command and options. So if we do want Stata to evaluate multiple lines, we should add these line extenders. You technically can just make an infinitely long line, but that makes your do files super hard to read. We can also add a note here. So we could say note and then add this information here. I'll explain this in a moment. And one thing you can do is add 2 lines of the note. So by adding 2 sets of quotation marks, Stata will print these as 2 lines. We can add a Y label. So in other words, what that does is it just ticks the Y axis. And the basic syntax here is we start at this value, we go to this value, and then this is the frequency of ticks. Now, in this case, this is specific to the spine plot. We've actually got 2 y-axes, as you might remember. Let's pull up the graph again. We've got 2 y-axes, as you may remember. And so here, I wanted it to be the one on the left. And in this case, I actually didn't want anything on the right. And so we don't need to directly do anything about that quite yet. But I did also want to fix the X label. And we'll go ahead and take a look at that here. So we have the same kind of approach. We say start at 0, go to 1, and then have this be your frequency. And I specify axis 1 to tell Stata which one to look at. And then in the case of this bit here, I'm telling Stata to actually remove a title. So there's these quotation marks with nothing in between them. So I'm telling Stata to remove a title that went with axis 2. And then on axis 1, I tell Stata to just print the title fraction, which is much simpler than what it wanted to print. And here, what I omitted was a general title that said the word Protestant, because that was the name of the variable, which is sometimes informative, but here, not so much. Finally, there's a couple more bits here. I add a Y title, so that's what appears here. And the next part is I toggle the legend a little bit. So I say ring 0. What that does is actually pile the legend into the graph area itself, which oftentimes is not the worst looking thing in the world. And it's a way to make your graph more concise. Position just gives a clock face position. So you can see here that the legend is inside of the graph, and this is about at 10 o'clock. Stata sometimes isn't very precise about that clock face, but here it does a pretty good job. I think this is nice rather than having the graph be made smaller by having this down here, which forces Stata to compress this part up here. And then we toggle the box a little bit. So we add this region suboption. This stands for line pattern. And we put this long dash on it. I make sure that the color is black. And then I like having a fill color for the box. So making sure that this is white so it stands out against the background. And that's kind of all that's going on here. Now, I know that seems like a lot. And of course, you can use that point and click editor or ask me for help on making nice graphs. But I think it's kind of cool once you've gone to the trouble of the analysis to learn a little bit of basic computer science and think about how you can make nice looking graphs. Now, I did promise that I would explain what this means here. So this is another case of using return values. And so you can see I put in this left tick and right tick. These are actually unique kinds of tick marks, and these tell Stata when you are evaluating this, go look for something like it's basically telling Stata, don't print this as the literal string of words r parentheses n, but instead go look for a quantity in your memory called rn. This is basically like using a local if you watch the publication quality graphics video to the end. And Rn is in Stata's memory because I've tabulated, albeit quietly, that's what this prefix means, qui for quietly, death penalty and Protestant. So among the return values of this cross-tabulation is this Rn, which is the sample size for people who answered something on both of these things. So that's useful because we don't want necessarily the overall sample size here because not everyone answered both of those questions. So we want to actually restrict what we print as the effective sample size to only people who answered these two questions. And rather than look that up and then have to write down by hand a number in our code, we can just do this and then tell Stata whatever you got from this pertaining to the sample size, just print it. And when I print hundreds, probably, at least a couple hundred graphs every semester when I teach this class, and I have the ends there and stuff, I'm not going and doing all of that by hand. That would be totally tedious. What I am doing is writing routines like this, where I don't actually have to look up the n. I just tell Stata to pile in the n from whatever you already printed or already had in your working memory. In this case, it actually doesn't print it. So I'm going to pause there. This is the end of the basic lecture on qualitative analysis, and I'll turn in future videos to a discussion of cases where we've got, for instance, a categorical or qualitative predictor and a quantitative outcome, and then even the tricky case where we've got a categorical outcome and a quantitative predictor. Thanks for watching. I'll see you in a future video.